Start பண்ணிடலாம்ல sir?
You can start. You can start.
Okay sir. Thank you sir. வணக்கம். Welcome to the day 2 of 5-day online FTP on additive manufacturing from 3D printing to factory floor. The speaker of the session is Professor S. Kanagaraj from IIT Guwahati. The title for the presentation will be 3D printing polymers and its composite for musculoskeletal disorder and endovascular embolization. About Professor Kanagaraj. Professor Kanagaraj is associated with the Department of Mechanical Engineering at Indian Institute of Technology, Guwahati, with 17 years of experience in teaching and research. He obtained his BE in Mechanical Engineering from Tyagaraja College of Engineering, Tamil Nadu in 1997 and PhD at Indian Institute of Technology, Kharagpur 2004. Before joining IIT Guwahati, he was working as postdoctoral research fellow in University of Aveiro, Portugal. He has supervised around 12 PhD scholars, 20 research scientists, 40 MTech and BTech projects. To his credential, he has filed around 14 patents and published around 200 research articles that includes peer-reviewed journals, conferences, and book chapters. He has undertaken 10 sponsors project in funded by DST, DBT, MHRD, etc. Currently, he is the center head for Northeast Center for Biomedical Research at IIT Guwahati. He is reviewer of research projects from DBT and reviews in 5 international journals. His area of research includes biomaterials, carbon nanotubes based nanocomposites, biomedical devices and implants, material characterization, prosthetic and ortho devices. With this brief intro, now I request Professor Kanagaraj to enlighten us with the insight on the title 3D printing polymer and its composite for musculoskeletal disorder and endovascular embolization. Over to you, sir.
Okay, thank you. First of all, thank you, Professor Dr. Dinesh, for having invited me for this session. Okay, so already there is a late, so before anything, I will just start that.
Okay.
Okay, fine. Okay, so I will be talking about 3D printed polymer and its composites for generally what we are working on, that musculoskeletal disorder and endovascular embolization. And before we go into that detail, we will see what are that different applications of biomaterials. Okay. Okay, so if you know that a biomaterial, it is something like a non-viable materials used for used to interact with the biological systems and going to do the function of the that joint or maybe that internal organs. Okay, so and we have taken that mostly we have taken for musculoskeletal issues. Okay, and before we go into that, we will see what are the different materials, biomaterials, which could be explored in a human body. Okay, you can see that you have a different variety of applications starting with head to toe. Okay, cranial, and you will see that the metal, polymer, ceramics are the different applications. As we are targeting about composites, we have taken as a polymer based composites. You see that this literature talks about what are the different materials could be explored. Okay, even one example, if you talk about that hip joint replacements, and you will find that ultra high molecular polyethylene can be used as an acetabular cup, and if you talk about bearing polymer on polymer, it is for finger joints and all where the load is not at all being applied. Okay, however, for load bearing applications, you will find a metal on metal, metal on polymer, and all like that. And wherever polymer is being used, you can, or even metal also it is being used, you can think of using that 3D printing technique. However, we are focusing on that polymer based one here. Even the bone cement, what is going to be filled within that implant and the bone and that intermedullary nails and all, it is just to transfer the load, compressive load when it is being applied over it and how it is getting clamped. So just you need to ensure that whether that this proposed material using 3D printing, whether it meets that the requirement as that of the existing system, like a bone, whether it is a compressive load or shear load or whatever it is, only that. If you feel that it could meet the requirement, then we can able to think of using that. And maybe as it is you are planning for a biomaterial, there will be a lot of regulatory approval and all like that. Maybe you can start with that where that products which are being used outside. Okay, that one of the component is that exoskeleton device. It is something laser of apparatus which can be used for joining the pins which is passing through the bones. Okay, in case where that implant plate and other things is not going to work at the same time, you also need to rigidly fix that bone. Then in that case you can think of using the laser of apparatus and all like that. Okay. And as we directly go into that musculoskeletal problem, and you see this one is mainly for a flat foot. Okay, so in a flat foot, you will find there are a lot of problems, starting with flat foot or maybe hollow foot. Okay, and when you take a pressure mapping, okay, this is what when you see that this is a normal pattern, though it is a normal pattern that a greater that a toe angle is more here. Okay, however, you just see more or less it is at a healthy foot kind of it. We can say that okay, it should be from central plane. It will be only about a 7 degree tilt should be there. Okay, and that the right foot is bit normal and left foot is inclined more. Okay, so if you assume this one as a normal foot, okay, you can see here at that mid foot, you will be having some kind of R. Okay, that you will not find in a case of a flat foot. This is for flat foot. The entire foot structure will be starting with the heel to toe, everything on the flat condition. Okay, it will be everything. Though the load may be get varied. Okay, and however, it is not a good for dynamic conditions. And this is a flat foot. And another extreme condition is here. Okay, another extreme condition is high arc foot. Okay, so sorry, something that's come. Okay, in a higher foot, you see that at the middle, at mid foot, there won't be any load acting on it. There will be just once you insert some paper kind of it, it can pass through from one end to another end. That is also not good. Okay, so in this case, how we can able to sort out the issue using that 3D printing? That's what we are going to see here. Okay, and this for conventional one is there will be a lot of this is for what you can say flat foot, and conventional you will find the silicon insole and the arch support insoles and the memory foam insoles and all like that. Okay, and we need to have if at all you are going to work on that a flat foot or a higher foot, you need to see this is that requirement is mainly for a flat foot only. Okay, you need to give some kind of arch support. Okay, and at the same time wherever you are seeing that a pressure, so this is a pressure distribution and this need to be distributed. Okay, so there will be a small loading on that midfoot and the pressure intensity at the heel and toe, it should be at par with a normal one. Okay, so that is what we need to do have. We need to have that pressure distribution and all like that. In addition, when the person is doing a heel strike, that time also we need to do that heel strike pressure also need to be improved. Okay, and this whatever the technique what we are proposing, it can also be explored for that diabetic foot also. Okay, so once you know that after all you need to have that pressure distribution only. So if you reduce the pressure at this particular point, then if you distribute it, anyhow that other portion may bear more load. However, as it is already in a damaged condition and it is better to avoid that loading, so we can able to have that pressure distribution and all like that. And for that, we have proposed a metamaterial based insole for a flat foot and OA and even diabetes and even for a osteoarthritic condition also. Okay. And here, so in this case, what generally we do, we take that pressure mapping of that particular patient and we will analyze where the pressure is supposed to be, where the pressure distribution is high and low. Then we need to make a pattern. Okay. And in this pattern, we need to keep some kind of, this is what the unit cell which works on the auxetic unit cell. So auxetic unit cell, you know, that is it having that, what you can say, negative Poisson ratio. Okay. So just one minute. Hello. Yeah, I'm in a meeting. I will call. Okay. Okay. This is for so when you are applying a force in both the directions, then what will happen in a normal conventional case? It will bulge. but being an oxidic material, so that will bring inside. So when you are compressing it, the side also will go inside. So you will be having the negative Poisson ratio. Okay. And by that way, we can able to this is a unit cell, and you can place it in a different location where you wanted to have that pressure distribution and all. This is what the plan. Okay, this is what the major distribution area. Okay, so in a hill strike, you need to distribute, and in addition, that where that arch support is required there also, and in the metatarsal portion also, you need to have pressure distribution. The same way you make it, and after all, this unit cell you cannot make it independent. So that should be something you need to make a composites. These are all unit cells are being made using a 3D printing, okay, SLA. And we need to make some integrated component. That integrated component we use as a silicon. Okay, so when you use a silicon at the same time, that entire composite will should have that characteristics. Okay, initially we have made this design, and after that we have made different design modifications so that the oxidative characteristics are not getting deteriorated. Okay, then after that, once we use it with the patient, then we can able to get more or less that uniform or healthy pattern fit. This is what is generally we did. We do take a 3D scanning of the flat foot, and after that we do some modifications on that profile whatever we got. Then after that, once you have that flat pattern, then we make a CAD model, and after that we did a 3D printing. Okay, this is with the FDM, we got it. Okay, exactly, it will give that a profile of that particular patient who we can able to have that. This is it can give about that foot support, arch support. Okay, and here you will be having a pressure distribution and all like that. And this is what we have used a 3D printer, and this is what that first. This is what that I said now, first design, and this is what that second design. And first design was not fulfilling the requirement, and after that we made this is origami inspired. Okay, so initially we made with a different paper size and how it will be, how much load it can able to bear, and other things we did it. Okay, and here also we made one with flexible, another one is rigid. Okay, so and with this is with the silicon. Okay, so after that we have made and we have taken, and after that once we ensured that it meets the requirement, then we got the mold, negative mold for the insole, and there in this one we have kept uh, that what you can say here we kept all the unit cells at the required place, and we filled that silicon. Okay, so that all the unit cells will be encapsulated with that, and you can see here are those. And when we need to have a both flexible as well as rigid, we keep two unit cells together. Okay, so here you will find two unit cells, soft as well as a flexible, and the rigid one. Then after that, that is the patient trial. When he is walking, we can able to see that the pressure distribution and all like that. And this is for that gate lab in which he has been tested, and this is for the full body marker where whatever kinematic pattern we can able to see, we do. Okay, and you can see here this is what our pressure mapping. This is that agent person is around 61 years old, and initially this is what this is what you can say stand space, and it's a normal, and this is a stand space at a maximum. You will find here is this normal flat foot. And see, you can see that a lot of silicon gel based and insole or memory foam, they are all commercially available. So we need to see how far it is going to work. So this is what we have tested it also for a commercial available one. Okay. Though it can able to do that a pressure distribution, you see here the pressure distribution is not perfect enough. Major thing is that that limitation in that existing one is it will distribute that pressure. Okay, there's no doubt about that. But here, when you are talking about foot disorder or higher foot or flat foot or a OA patient, osteoarthritis patient, we need to have a selective pressure distribution. Okay, that we can able to manage it, and this is what with the one leg we have initial trial made initial trial, and here in this case you will find that support in the form of arch support. That's what you will find that stresses also, and this is the normal silicon gel. Silicon gel. Okay, so after that we have made two things. And this is with only one foot. You can see here. This is a barefoot for a flat foot condition, and we have used only silicone insole without any unit cells. Okay, you will find not much changes, and this is what is commercially available. Okay, and this one you can able to see what is a composite insole with the unit cell as it is carrying. You can see here, this is what where we need a uh, arch support so that the flat foot will not be there. However, in the rest of the cases, in a silicone insole as well as commercial insole, there's no support. It is a distributing the pressure in load intensity. That is perfect. However, where we need to give a support, that cannot be provided. However, we can ensure that where we are giving the arc support as well. Okay. And this is the same thing. Okay. And here you can see that comparison. Okay. And this is what the peak pressure at front foot, and with the back foot, you will find that near about a 45 Newton per centimeter square. And once you use a commercial as well as silicone insole, it got a pressure distribution, it got reduced. That a pressure is giving a pressure distribution. That is perfectly sure about it. However, when we use a composite insole, it is getting decreased from 45 to 25 around that. Okay, and at the midfoot where we need to give a support. Okay, this is what that maximum pressure what is acting there at the midfoot. Okay, and we can able to give this support from about 18 to around 25 or something like that, 25 Newton per centimeter square. And at that metatarsal foot also, sorry, at that heel strike also, you can able to reduce that pressure distribution. Okay, and this one is just after a 2-3 days we have given we have taken test, and if the patient is allowed to do walk maybe about 2-3 weeks, then we can able to have a perfect synchronization and perfect expedition. And this one, this is just with the insole when he is walking, and we kept these insoles inside. Okay, inside the shoe, and where we can able to see that front foot and midfoot and heel strike. We could able to see that there's a pressure reduction at the heel strike and the midfoot. Pressure at forefoot, and at the midfoot you have greater support. So what will happen? We cannot see that when the flat foot is there, that is not an issue. It may not be an issue, but it will be having cascading effect on that rest of the joints and all like that. And other one is for osteoarthritis. Okay, so this is what Endolite and Autobux they are making it for a osteoarthritis patient, and here the thing is that this is something a normal mechanical system only. Okay, so it is a 3-point system, loading system, and when two side it is you're applying the load, then there will be a reaction. When the reaction is coming this side, then there is a gap between that. It means when you are talking about osteoarthritis, it means that when femur as well as the tibia is moving, always there is a gap between the femur and tibia. In between, you have a meniscus and the cartilage that helps to avoid the bone-to-bone contact. If the cartilage is broken or cartilage is damaged, and there is a chances of if then entire load will be coming to the meniscus, and that also will get damaged, then there won't be any, what you can say. Then if it is severe, then apart from surgery, there is no other alternative. Okay, so if we could, and sometimes all the patients are not fit for surgery, and some people they may not be interested to go for surgery also. So in this case, what can be done? Not for a severity cases, and when you are identifying that a severity level 1 and 2, only in a 3 you will be going for a surgery, and severity level 1 and 2 or that preliminary stage, if we could identify the osteoarthritis conditions of the knee, then we can able to just by the same insole what we are proposing, then with that we can able to give a conservative treatment. In addition, this is that knee brace also, this also can be used. So here what will happen once this is under fabrication. Okay, we have not tested this device. Okay, this device, once you fix it, what will happen? Suppose you are fixing it here. Okay, so at the medial side. So when 2 direction load is being applied, this direction will be pushed. Okay, and you can able to ensure that the same way you can able to have that gap. One thing. And second one, that load we using this one, you are uh, this one you are shifting the what you can say knee axis from medial side to the lateral side. In most of the cases, if you see here, if you do that statistical analysis, and that medial side will have a more damage compared to that of a lateral side. Okay. So near about 80% damage mostly on a medial side compared to the lateral side. So if you shift that load line from medial to the lateral, okay, first thing you are not damaging, you are not applying a load on the damaged portion. In addition, as you will be wearing this device, and in addition, you will be what you can say, you are not applying a load and you are giving a gap. So what will happen if at all it is identified in a preliminary stage, then the cartilage may try to regenerate by itself. See, cartilage generally it will not be, regenerate, but that also there is some threshold. Beyond that only it will not regenerate. If some damage is happening within the threshold limit, then they may start to regenerate. So you can delay the surgery or you can avoid the surgery at the later stage. Okay. and and this lab, that whatever we are working on it in this gate lab, we can able to diagnose the condition of the osteoarthritis and even the severity level. Okay, if the person needs to go MRI for to confirm the surgical requirement. Okay, so for initial stage, you no need to go MRI if at all the person is having that knee disorder, mainly osteoarthritis. Okay, so this is what two devices in which we have been working. The first one is when a person is having the osteoarthritis, it will generate some acoustic waves. In a normal case, also it will have some waveform. That waveform, that frequency will be around 1 kilohertz. At the same time, when a person is having a osteoarthritis, the frequency could be around 10 kilohertz. So if we could capture the sound waves which are getting generated from the knee osteoarthritis, then we can say that what is the condition of that knee. It is something like how cardiologist is or a cardiosurgeon is identifying the heart problem using ECG. The same way that an orthopedic surgeon can identify the condition of that knee. Okay, just by seeing the wave pattern of this. Okay, then this is one technique, and another technique, this one with a deep squat condition. Okay, so if a person is in a good condition of the he has good knee, then that he can do that. What you can say? Uh, he can able to do that squatting in a better way. Okay, even that angle could be around maybe like around 30 or 20. That is whatever the minimum that up to that he can able to do the squatting position. But when a person is having a severe or a mild osteoarthritis conditions, then that knee angle could be, it will be more. In this case, this is that condition of that. In this case, the doctor suggested for a surgery, and the patient is not willing to go for a surgical condition. So not is not willing to go. So this is what maximum he can able to do. She can able to do. It is about what you can say about 100 degree or something like that. So we are working on correlating between that gait parameters as well as that MRI, so that MRI can be used as a basic standard, golden standard to confirm the osteoarthritic conditions. However, we can supplement the data in one, wherever that MRI is not required, we can only with the gait data itself, we can able to help the doctors to augment his decision making process. That is what we can. Okay. And the same thing we can see that, and in this case also, what we are suggesting that for shifting that load line, we can use this device. Okay, that knee brace. This also it's a 3D printed because there's no load is acting on it. Okay, so we are by using this device, this 3D printed device, just to shift that load line from medial to the lateral or lateral to the medial. Okay, so where, as I said, this is not a load bearing one, so you can able to think of it. Okay, and this one, even with a normal conventional shoe, we can in the shoe where we can play with that insole. Okay, and even sometimes that walking pattern or when we use some kind of a shoes, sometimes we compromise. Okay, we will go to the shop maybe after a month or something like that. Till that I can manage. So that makes a lot of problem. Okay, for some people you can see here. Okay, initially it is in a normal case. This is, you can see these conditions. Okay, in there maybe you might have seen that some people, they that, yeah, greater toe will be very close to each other. In a normal case, it will be from the parallel vertical line. It should be around 7 degree. Okay. In few cases, in this case, it is not maintaining that 7 degree. Okay. And in this case, we have suggested to replace that insole. It can be 3D printed or it is commercially available one. So after giving a training and after replacing her shoe, then we could able to, this is after a 3 months training. 3 months suggestion follow, then we could able to see that a 7 degree tilt toe out. Okay. And the pressure distribution also we could able to find it there. That also. Okay, this is only with the physiotherapist and the engineering approach we could able to sort out the issue. And the only thing they have changed that what you can say insole. That is, in this case we have used a commercial available one, and the training, walking training we had given in the gate lab. Okay, and that the pronated foot. You can see here in this one. In this case, as the leg is little bit up tilted, you can see that at one mid portion that a person is not having any load. Okay. And after the shoe correction, that mostly it is a insole only what we are working on it. Okay, and that is either commercial or a 3D printer. We prefer whichever is available for him and suitable for him. Okay, then after giving a suggestion and a training, we could able to ensure that is, this is all the data what we took. It is after 3 months period of time. Okay, this is, you see they are at C is around how much? Around 31 or 32, one of our students, and C is one of our colleague, faculty members. Okay, so we could be able to see that age around 45, and we could within 3 months we could able to correct it. Okay, this at just after that. So that this one we should not see as a problem from only one aspect. As you know that when our foot is trying to adjust the distribute the load in a different pattern, that will have a effect on the ankle joint, knee, and hip, everything. And if you see that their walking pattern, that pelvic tilt and pelvic rotation when they are walking, it will be totally, it will be different. So that is what the loading pattern will not be synchronized with the healthy people in that case. And this is another 3D printed component. This is that insole, sorry, what is the AFO, ankle foot orthotic device, and this what we have commercially, it is what it is available in the market. We have taken it, and this patient is having a foot drop problems. Foot drop problem means, you know that in ankle we will have a plantar flexion, dorsiflexion. Okay, so in dorsiflexion they can do, in a plantar flexion they don't have any control over it. So this all that component what we have made it, we have designed it, we did a 3D printed and a spring controlled mechanism. Okay, so that spring will hold that energy for that foot drop problem. Okay, then after that we could able to, after 2 weeks time. Okay, this we have taken based on that normal video camera. It is, he was not tested in the lab. Okay, and after that his pattern was at par with that sound line. Okay, that is a spring controlled mechanism only we have designed, and these are all what is some kind of orthotic device what is commercially available in the market. In this device we have something we have fit based on his conditions. It is only we have made the spring loaded mechanism, nothing, simple device we have made it. Okay, so the problem might be severe, but we try to do something simplest possible solutions. That's one, nothing more. And this one, just I thought of sharing something also. Okay, and this is recently I saw one paper in Nature. Okay, and this also that you just it is a unit cell based. Okay, and this unit cell based, you can see here this is a Nature 2000. It is only in August last week only it got, about 10 days back only it got published. Okay, and this is Caltech, this paper from there. Okay, and you can see here this is what the unit cell approach. The same thing, whatever we were working on that different unit cell origami based, origami inspired metamaterial, the same thing they have used it also. Okay, and this you can able to ensure that how much weight it can able to bear and without any support. The same material is being used as a support, and only the major problem is that this material might not be good only at the shear condition. However, it is normal bending and tensile and compression, it can work. I don't know about the tensile, how far it could be, but in compressive, it will work very nicely. And shear, it will not work. Okay, and they did some bending stress analysis and all like that. And this in a fabric form, they can able to use it in a different. And this you can see that though it is a symbolic, this one where a car and a truck can able to travel over it up to that. Okay, and this we can use it for the people who are having the scoliosis or maybe the spine disorder. Okay, so we can able to give a spine support for those people. Okay, so the thing is that you can play with your requirement. It is not that you need to have that entire bearing strength or entire loading characteristics up throughout its area. Okay, so you can select your requirement. The commercial available one, it is the major problem is it will distribute throughout, though that it is not the common requirement. However, there is no other alternative. That is what people are using it. In this case, you can select your own, like what we did it for insole, even for osteoarthritic, and even for weight bearing. You can see that weightlifting person also he can use it, and here also we can able to use it. Okay. Oh, just 1 minute. Ma'am. Hello. Yeah, ma'am. Actually, instead, yeah, yeah. Yes, ma'am. Actually, instead of a Dr. Bora, if you arrange someone to attend it, that will be good. Otherwise, if you are joining also, that will be good. They may ask some query, you please clarify. That's all. Nothing more. No, whomever you are interested. Whomever you can just talk with the doctor who are not in OPD. You just call them so that the committee will be agree with that. Okay, because from medical, nobody there. I'm in a meeting. As soon as it is over, I will call you back. Okay. Thank you. Oh, sorry. Okay, this is what I was suggesting. Okay, and this is that unit cell, how it will be looking like, and how they are locked. And in our case, we have done in our case whatever I was telling here. In this case, we have just separated it out. Okay, and we placed it, and we have used silicon as a bonding agent among all. And here they have used interlocking mechanism. Okay, so they can directly you can use it, and even if you are if you make a fabric or if that this you can directly use this product kind of it. Okay, depending on the requirement. Fine. And how that bending modulus and the number of contact, how it will be varying and all, it is there. Okay, so you can see those papers that was recently published. Okay, fine. And these are all where we have used all those unit cells, we have used it. And apart from that, whenever we are doing some kind of a initial prototype and all like that, we do 3D printing. Okay, so with mostly we do the FDM technique only, and even this is what the knee what we have been working on it, and it has gone for a different trial, different level, and this is only that commercially it is we have made in normal conventional manufacturing, and this one we have made using vacuum casting. In a vacuum casting, you need to have a 3D printed mold. See, you might have seen that in a conventional technique, conventional polymer processing technique, generally you can go for injection molding and you will have a die and you can get it done. But the die is a mostly expensive part, about 5 lakh or something like that, depending on a number of components. But here in this case, if you go for a vacuum casting, you no need to have a big mold and all. You just make a 3D printed with a different surface, whatever the required surface finish, then you can think of how it could be used. Then 3D printing technique, you can get the die and mold, and you can able to do it in a vacuum casting. You can able to get the product. Okay, this is what just I thought of saying. And this is another knee joint. Initially, we do this is for ankle joints. One is with metal, and this is for a dynamic one, dynamic ankle joints, which can give a support during uneven walking surface. And this is final product, and this is at initial stage we make all those 3D printing technical. Okay, so for initial trial and all like that. Okay, and this is a liner and a liner product and all. And this is what just I thought of showing it. Okay, this is what the third version of the knee joint in which we have been working on it. It is having the TK alignment for normal TK alignment and the vertical and horizontal link length. Okay, it means it gives that we can able to use it for different people with different load line correction. Everything is possible. In addition, this also having a knee rotation option. Okay, you can able to bend or kneeling down, everything is possible. And initial design and prototype, all the 3D printing only. This is what you can see here. Okay, 3D printed technique and maybe afternoon बाद में आएंगे तो हाँ ठीक है हाँ हाँ ठीक है Okay. So this one we can able to give whatever that I said sometime back, the plantar flexion, dorsiflexion. You can give, it needs to give about a 35 degree. So this is with the ISO 328. Okay. So we need to, for when we are designing the ankle joints, these are all 3D printed only. That's what I thought of showing it. Okay. However, this can be used as a prototype. It cannot be used for a testing device. And when, as you are talking about the 3D printing, we will come back to that socket making. This is mainly for what you can say, 3D printed socket which can be fit with the residual stump of an amputee. Okay, and this is what initially we will take the scanning of that particular person. This is that residual stump, this is a knee, and this is where that leg got amputated. Okay, and after that, which portion we need to address, that we will be highlighting it. Okay, then after that, once we get the data, we will be making the design, and we will do that design analysis like that, how it will be inserted. And in this one, what will happen, we will ensure that the entire portion is bearing the load. In most of the cases, whatever that conventional process, that is negative mold, they will making a POP bandage, and after that, first they will make a negative mold and they will fill that POP, and they will get a positive mold, and from that, over that, they will be making a socket using a trap method, or they make a composite, fiber reinforced composites and all like that. So in this case, this is expertise from the prosthetist is more important. Okay, so you may not ensure that how the load is getting distributed within the residual stump. That is what, once we do that, then we will do that all the analysis and all from that, and we can, the thing is that once we get that scanning MRI data from the of the residual stump, from that we can able to design the residual stump, and this also we can able to match with 3D scanning. Okay, so we need to have MRI in a direct socket fabrication system. We use that one only. So we take a MRI and we take a 3D scanning, and we both will superimpose it, and where we need to have a constant pressure over the residual stump, and after the once it's made everything, then we'll make a socket using a 3D printer. This we have made with Status FDM. Okay, then where you can get about that quality whatever you want. Only thing, it is a bit expensive. Okay, then after that we have tried with a patient. Okay, for the residual stump. And this another patient also for whom we are making right now, we are working on it. Okay, the thing is that this is what from the MRI data, what we have got, that he's a bone conditions. Okay, the thing is that his bone, he is an army person. Okay, so initially just for a life saving, they did exactly knee articulation. However, the bone inside it got fragmented like anything. Due to that, whatever the socket is being used for him, it is not, he is not getting comfortable. Okay, So we have started to make some kind of socket. So this is a misplaced. Okay, this socket. So what we are planning, so this entire portion, it will not bear any load. Okay, because if it is a load is being applied, then what is the condition from that neighboring bone structure? It needs to bear the load. Okay, so in this case, that 3D printed and one it will help. So here we will be ensuring that are in this way, in this location. So all the attachments, whatever the residuals that socket will be making, and that starting point and the load concentrated will be at this portion only, because below there won't be any load bearing application. This below that part, that residual stump will not bear any load. Okay, so it has been fused like anything, and the doctor is not willing to do further surgery to correct it. Okay, it will be risky and all, he was telling. Okay, so we are not going into that. What we are saying is that our socket design will be in such a way that it can able to, that loading entire support will come from that femoral neck portion. Okay, then only we can ensure that the load is perfectly getting a transfer. Okay, fine. This is where that our 3D printing of the socket making will be very much useful. Okay, and another, this is what recently we have made a trial on that knee joint, and we could able to get that pressure distribution and all. Okay, this is a before and it is after. You can see here in the toe off conditions, he is not having what you can say, he is not having putting any load, because in normal case he is doing not flexing the load, not flexing the knee. So that is what, once he flex the knee, then only that foot will bear the load. That is, you can see here also. And this is what the trial for the rehabilitation, whatever that product you are making, 3D printed socket and other things, we will be testing it, how far it is giving a better performance over to that walking condition of that particular person. That's what we will be testing it here. This is what I said. And this one is what you can say, this one is a human model cochlea. Okay, so this is made with the SLA. And why we need it here, this is what we are working on, cochlear artificial cochlear implant. Okay, the basilar membrane. Okay, with a different length. After that, based on that pattern, whatever we are getting it. Okay, so whatever we will be getting that sound wave, how much it is a decibel level he can able to bear. So based on that, we can able to design that length, width, and so only the length and width is fixed. Only the length will be depending on that how much he could able to hear. And in addition, once you are, when that cochlear implant is getting inserted within the cochlea, that inside there is a pressure distribution. Okay, sorry. Hello. மீட் பண்ணிருக்கேன், அப்புறம் கூப்பிடுறேன். Okay, bye. Okay, so how much pressure is it can able to generate when the electrode is in, though it will be about in terms of Pascal. Okay, but it will be having a lot of cascading effect. Okay, and this thickness and all, we can able to think about 400 micron, 400 nanometer, 100 nanometer, and all like that. These are all piezoelectric thin film kind of it. Okay, and here we have used SLA to get that cochlea. This is 1:2 scale. Sorry, 2:1 scale. Okay, so we can able to make it. And this is for a testing one. We made this device. This entire prototype is made of a 3D printing technique only. This will give that electrode insertion, and where we can able to see how much pressure is getting generated when the electrodes are getting inserted. You can see that these are in a Pascals. So when insertion velocity is more in cochlea, okay, so the pressure will be more, pressure generation will be more. That will be something like a bomb blast kind of it. So this device we have made it using that, and this also additional device, switcher closer device. This also we have made a 3D print. Okay, this what about different biomedical device and musculoskeletal disorder, and we will go into the endovascular embolization. Okay, so in endovascular embolization, here also we have used a 3D printing technique only. So where we have, just we will discuss it. Okay, so this one embolization, endovascular embolization means suppose when we talk about our blood vessels, it might be strong and it is high viscous, high elastic in nature and all like that. That is what even when you are talking about open heart surgery, when what you can say, some blockage is there in the coronary artery, they will take a blood vessel, part of the blood vessels from the leg and they will be fixing it. Though it will be of a different diameter, but it's as it is having high elasticity, so we can able to what you can say the pulsatile pressure, pulsatile flow can be accommodated, even though the diameter is less. Okay. However, in that blood vessels, if due to some reason there is some kind of stiffness is getting lost. Okay, so in this case, you can see stiffness is lost. That is what it is. Balloon formation will be happening. Okay, this is what it is when the balloon formation will be happening. This is called aneurysm. Okay, so here in the existing one, the all metallic coils are being inserted and they are filling that cavity in that aneurysm. Okay, so that the purpose is to arrest the blood flow into the aneurysm so that bulging will not be happening. Okay, so as the requirement is to arrest the blood flow, why do we need to think of using the metal? So why don't we go for a polymeric metal? That's what we have gone through that approach. Okay, as you know that being a polymer, their radio opaque is poor. So we need to add some radio opaque material like a barium sulfate or hydroxyapatite and all like that. Okay, so that is what our research went in that direction. Okay, from statistical point of view, with this, so about 6 million or 1 in 50 people in United States have unruptured brain aneurysm. You see here, at this particular point, when if it is not, the major problem is it is not getting diagnosed. If at all it is diagnosed, it is by accident or it is by the person is lucky enough to be identified. Okay, because it will not, it is in the brain mostly, mostly it is in a heart and brain, it is what it is a danger. Okay, in other places also it is there, but here it is a most, okay, so mortality is, morbidity and mortality is very high in this case. If at all it has happened in the heart and recovery also, it will be very less in this case. Okay, because after that, there is a lot of complications after that. Okay, so that is what it is. And if at all it is getting burst, then what will happen? Brain hemorrhage and other things will be happening. Then due to that, the patient may not able to survive. That is what the case. This is a statistical data about and a number of near about 5,000 deaths worldwide every year. Okay, and that's what 2 out of 3 people with a ruptured aneurysm. Okay, they die before arriving to the hospital, and even that one person is getting is survived, he may have a lot of neurological disorder and all like that. Okay, and what are the different options available in front of us? It may be of this is whatever it is going to be filled in that aneurysm, it is called embolic agents, and it can be of a liquid or a solid, or it could be of a particulate. Liquid, this is what the Onyx, what is commercial available. This is a liquid gels. If you insert, just you need, once you do the radiology and all, if you get that radiological images, you can calculate what is the aneurysm volume. So if you use Onyx and all, then just to put, suppose the volume is about a 3 cc, and your this Onyx material you need to drop at only 1 cc only, 1 cc liquid. If it is injected, then it will once the material is in contact with the blood, then it will start to bulge. Its size will get increased. Then it can able to fill that entire aneurysm. That is what it is. Okay, and other materials and all, even in ethanol and all like that, that is also, it is just, it is something killing those cells and all like that. Okay, and other mechanical devices are this one. These are all other some liquid and gels just to fill that aneurysm. Okay, but these are all not that much. Onyx is the commercially it is being used for a long period of time. Okay, and mechanical devices, you will find that mechanical coils that is getting inserted into the blood vessels. It will reach that destination and it will cover that entire aneurysm zone. Okay, Then balloons and plugs are, it is an external fixation device. Okay, so here you are not accessing the, you are not going into the blood vessels, you are accessing the blood vessel and you are using some kind of a mechanical clip or balloon, something like that. Okay, however, that is not going to work if at all the blood vessel is not going to be easily accessible. Okay, because mostly it comes in that arteries only. Okay, in the arteries mean generally it will so deep inside. Okay, so it will be very difficult to access. In that case, this mechanical device apart from coil will not work. And in particulates, the PVA and all that, is agryl gelatin and all that is being tried. And in one case, if it is spread in a wide area, then they will go for the PVA and all like that. This is what I was telling about it. This is a clip system. If it is accessible, then only they will use. Okay, so that the blood flow into this aneurysm will get stopped. And you can use that bypass this blocked portion and stop that this one, and from here you can able to bypass from here to there. Okay, or you can do the grafting. Suppose if this is the case, then in that just to cut, remove, and you can use some kind of a graft material and you do the stitching, and so that blood flow will be ensured. Okay, till that you can see that some temporary supporting device can be used. So you can clamp, you can fix it, you can complete the surgery, then after that you can release it. That is possible. And here, in this case, you are, this is all it is outside you are doing something, and here that coil it is you are inserting through the blood vessels to arrest the blood flow into that. This is for 1x, how it will be looking like. Okay, these are the different things and all. And this what you can see that when you're doing that angiogram and all like that, this is what just 6 aneurysm, and after 15 days, 13 days, it got increased to 14 6 to 14 So like that, because this is the brain structure, the blood flow to the brain stream was taken. Okay. And what we did it, instead of filling this coil, you instead of filling the aneurysm with a coil, why don't we think of using the polymer based one? Okay, in a polymer, what is there? There may be so many other alternatives. So, how do you insert that polymeric material inside? Okay, so here that we have used a shape memory polymer. Okay, it is a smart polymer. Okay, in the smart polymer, first we will take that exact volume of that aneurysm, and for that volume, we could able to see how much we need to insert it. Okay, first we will take that shape, and with a shape memory polymer processing, we will get that shape of the exact shape of the aneurysm. We will be taking it. Okay, then after that, bring down to the less than transformation temperature and make the temporary shape as we will be attaching it with the normal catheters and all like that. Then after that, that catheter will pass through the femoral artery and go to the desired destination. Okay, as that external stimuli in this case is nothing but a temperature. So as soon as it is in contact with the body, bring that body temperature, then it will come back to the original shape. So before, within 5-10 minutes, that implant, whatever it is going to be used with a 3D printing, that need to be that 3D printed shape memory polyurethane. That will be filled within that zone. Okay, then after that, once the time goes, then they will be trying to bring the temporary shape to the permanent shape as that of the aneurysm. Okay, then you will be stopping. Then a blood flow into that system will get stopped. This is what how we are doing that. And this one here we have used what you can say shape memory polyurethane, and with a filler initially we have used a tungsten, and after that we have used tungsten as a radiopaque material, and after that we have used what you can say barium, nanobarium sulfate and nano hydroxyapatite, okay, as a radiopaque material. And here we have used a porogen also. In the initial trial, we have used a sodium chloride. Then after that, the polymer with their dispersed in acetone, and after that, we have mixed with manual mixing, and after that, that's the coating, coated the polymer coated with filler and the porogens. Then we will get it processed through the twin screw extruder. You will get in the form of wire, and that wire, if you pass through the pelletizer, you will have a different pellets. That pellets we have used it for in case of compression molding as well as injection molding for that product characterization and all like that. After product characterization is done, then we have taken directly the filament. Okay, this filament, whatever we are getting it here, that directly we are getting it and we are processing through that 3D printing technique. Okay, and 3D printing technique, whatever it is done, then we do that a salt leaching technique. Whatever the porogen is added, we have removed it here. Then that we have tried it for in vitro studies and all like that. Okay, we have the different shape, we got it. Okay, this is what that exact one is. This is scaled one. Okay, aneurysm and web-like structure and lumens, whatever that blood vessel size is there, according to that we have made it. Okay, and with this is, and one of the major problem is that this polymer shapemery polyurethane, okay, it is having a what you can say, hydrophobic characteristics. As soon as it absorbs the moisture, what will happen? Its the glass tension temperature is getting drastically reduced. We want to have the glass tension temperature at 35 or the transition temperature. If it is low, what will happen? Even at that normal temperature, above that point, then it will come back to the original shape. So what we did during the processing, we made one a temperature chamber. Okay, so with a Peltier attachment up to about 18, it can go up to 18 degrees. Then after that, we process this one to get the desired shape. Okay, then these are the filament, pure filament and porogen filled filament and with tungsten and radiopaque. Sorry, tungsten is a radiopaque material and this is a porogen material. Okay, and we got a different shape and we did a shape fixity and shape recovery test we have done at a 40 degrees centigrade. Okay, so we could able to ensure that more than a 95% shape fixity and shape recovery could be ensured. And some product testing and all like that. Okay, so we did with a salt filled sample and after salt leaching, and this is with a tungsten filled sample and after salt leached out sample, so that we can able to see that under X-ray. That is what is our plan. And here in mostly we did in vitro test and we have confirmed that shape recovery characteristics. And you can see here we have made about a 1 centimeter cube sample. We have made it with a 3D printing. And after that, we did a temporary shape by compressing one of its side to 50% and we have kept it at 60 degree and with a different time interval. You can see here at around 305 minutes time, the sample got reached its permanent shape. Okay, and this at 60 degree, and if you do at a 40 degree and all, we can able to go more than a 5 minutes because this is time it is required. Because that once the implant is inserted, we need some time to reach the desired destination, and that expansion process is supposed to start after reaching the destination. Otherwise, that reaching the destination will be an issue. That is what it is. And this we did with the radio pack materials and all like that, and we compared with the existing radio. This is what the 1x and this is a tantalum powder, and this is what is commercially used platinum wires. Platinum wire which is used to fill that aneurysm. This is what the radio pack, and we have compared with the composites. Near about 12.5% of barium sulfate, it gives that at radio opacity at par with what is being used in a conventional materials. Okay, the platinum wire. And we did a shape memory test and all like that. This is maybe paper oriented, and this will give overall view about what we have done and all like that. Okay, and we did some in vitro studies, and we have made with the silicon. Okay, and silicon we did, and we have made an artificial aneurysm, and we did in vitro study, and where we have confirmed about that the performance shape memory recovery. Okay, with that, I would like to acknowledge all my students and our funding agency and my collaborators. Okay, and with that, I would like to thank you. If you have any questions, you please.
Participants, the session is open for questions. You can ask clarify your doubts from Professor.
Yeah, there is something in there in the chat box. Oh,
Definitely.
Hope you could follow that whatever I was talking.
Participants, if you have any questions, I can clarify. I think they are in cloud nine right now, even because like I was just visualizing each and every slide, what is happening, being there and working with you in lab. Still, I'm admiring what are the presentation you have made. It is completely unimaginable. Now people would have got a mindset like they can take a surgical knife and go for surgery and something. That type of
See
insight
that
we
the
got.
thing is that we have used a 3D printing. We do have the facilities, even the 3D
Yeah.
printing metallic and the 3D printing polymer. In the polymer, we have I don't know what. Oh, just a minute.
Yeah.
Hello. Yes, ma'am. Ah, yes, ma'am. Yes, ma'am. It's 11 o'clock only, na? Yeah, a PPT has been shared. I am in a class. That's what I will be joining about right away. Anyhow, it is half an hour. Na? I can join after the class. Class is going on. 11 o'clock only, na? I will be joining 5 minutes before. 20 minutes. Okay, okay. Fine. Yeah,
Thank you,
sorry.
sir. Thank you so much. Because like I know personally, I know how busy you'll be there. Thanks for allotting the session, and moreover, you told me before as well. Like we have things, and what are the questions I have? I'll post you. Like even post session, we'll have a discussion, and
Yeah.
thank
That will be better. Okay,
yeah.
sorry. Okay.
Uh,
Yeah,
cool,
just now
sir.
I got
Like
a call.
I'll listen to the participant and let you know what are the doubts they have, and
Fine.
hopefully,
Okay then. Okay. Thank you.
thank
Thank
you,
you
sir.
very much.
Thank you so much.